Hi girls, today we are going to see about resonance in series RLC circuit. RLC circuit means resistor, inductor and capacitor which are connected in series. You see this diagram. Here we are having all the three components which are connected in series. So it is called as RLC series circuit. And what do you mean by resonance? Resonance means when the frequency of the applied alternating source is equal to the natural frequency, that is 1 by square root of LC of the RLC circuit, the current in the circuit reaches its maximum value, then the circuit is said to be in electrical resonance. That is, we are applying an AC source that should be equal to the natural frequency of the RLC circuit. Then the current will have its maximum value, and this phenomenon is called as electrical resonance, and this frequency is called as resonant frequency. And here when you see this diagram, we are giving an alternating source, and this alternating source frequency must match with the natural frequency of the circuit, because the RLC component will have its natural frequency. Both of them must be equal. In such a case, the current in the circuit will be maximum and the circuit is said to be in resonance. That is the main concept of this part. And here the resonant angular frequency omega r is equal to 1 by square root of LC. That is the formula, and L is the inductance, C is the capacitance. And you know F is equal to omega by 2 pi, where F is frequency and omega is angular frequency. So F is equal to now 1 by 2 pi square root of LC. And when you take the particular case as a series resonance, omega r is equal to 1 by square root of LC, where r here refers to resonance. So here when you square both the sides, omega r square is equal to 1 by LC, or you can write this equation as omega r L is equal to 1 by omega r C, and omega r L is XL and 1 by omega r C is XC. And you know XL is inductive reactance and XC is capacitive reactance. So inductive reactance must be equal to capacitive reactance at series resonance, and this is the condition for resonance circuit. And so this is very important, that is XL must be equal to XC. Since they are dependent on frequency, by varying frequency you can change, you can get the condition as XL is equal to XC. Next, effects of series resonance. So when series resonance occurs, what happens? The current in the circuit becomes maximum. So this is shown in the resonance curve graph, and here when you see the impedance Z is equal to square root of R square plus XL minus XC the whole square. And so when XL is equal to XC, square root of R square, so that will become R. So the total impedance of the circuit must be equal to resistance at resonance condition. So when you draw a graph between frequency and current, for smaller resistances the curve is very sharp, and for larger R the curve is not such a sharp. So it should be noted that the resistance must be kept very small, so that the current is maximum. So you already we have this relation, that is current is inversely proportional, that is current must be small if the resistance is large. That relation you already you know. And here when you see the current equation, and according to Ohm's law, I is equal to V by R. So Im is equal to Vm by and square root of R square plus XL minus XC the whole square, and you can replace this by Z, that is the denominator in this equation is nothing but impedance. So when XL is equal to XC, Im is equal to Vm by R, because the term get cancelled. And so here for smaller resistance, larger current with a sharper curve is obtained, and vice versa. And next we are going to see about the applications of series LC resonance circuit, and mainly they are used in tuning circuits of radio and TV systems. That is, when you see at air there may be different frequencies, and we are going to receive a particular frequency. For that you have to change the variable capacitor. So here I have shown you the variable capacitor. So the tuning is achieved by varying the capacitance of the parallel plate capacitor. So the resonant frequency also changes. and this resonant frequency is nearly equal to the frequency of the signal of the particular station, and the amplitude of the current will be maximum in such a case. Thus the signal of the station alone is received. For example, if you tune a radio for a particular station, for example Trichy station, then what will happen? In air the frequency will be there, and we are setting our receiver for that particular frequency, and if the resonance condition takes place, the current will be maximum, and at maximum value of current you can get the circuit tuned. And how can you achieve this resonant frequency? By varying the parallel plate capacitor, and so this is the capacitor. This value can be changed so that the particular frequency is got, and so actually you are matching your receiver with the frequency of the particular station. So at tuning, the frequency of your receiver and the frequency of that particular station will be same, only then the current will be maximum. This condition is called resonance condition, and you can receive for example in TV and radio, by tuning your receiver you can get particular frequency. Next, quality factor or Q factor. So when you take at resonance, the current in the circuit is maximum, and so the voltage across L and C are also increased, and we are going to see how much it is increased. So what is quality factor? It is defined as the ratio of voltage across L or C at resonance to the applied voltage. So here Q factor is the equation is voltage across L or C at resonance divided by applied voltage, because so many times it will increase. And so here when you see Q factor, what is voltage across L? That is given by IMXL divided by IMR, and so here you already know XL is nothing but inductive reactance, and so since voltage V is equal to IR, so we are substituting IMXL divided by IMR. IM get cancelled, so XL by R. And what is omega RL? XL is capacitor inductive reactance, and inductive reactance is having the formula omega RL divided by R. Here the suffix R represents resonance, and so here when you substitute omega R is equal to 1 by square root of LC, the equation becomes L divided by R square root of LC, and in the part of numerator L can be written as square root of L into square root of L, and already one square root of L in the denominator, both will get cancelled, so you will get the equation as 1 by R square root of LC. This is called quality factor. So actually quality factor means how far the number of times the voltage across L or C is greater than the applied voltage, that is called as quality factor. So this gives just the magnification of the applied voltage. Power in AC circuits. Here what is power? You already know this definition. Power is nothing but it is a rate of consumption of electrical energy in that circuit. So power is a rate of consumption of electric energy. So how can you calculate power now? And you know V is equal to Vm sin omega t, and I is equal to I sin omega t plus phi, where phi is the phase angle between V and I. And so you know the formula for power. Instantaneous power is given by instantaneous voltage into instantaneous current. So you can substitute that. So instead of V, Vm sin omega t, and instead of I, Im sin omega t plus phi. And so here when you expand this sin omega t plus phi alone, you know sin of A plus B is equal to sin A cos B plus cos A sin B, and so sin omega t cos phi plus cos omega t sin phi, and you multiply sin omega t inside the equation. So Vm Im, and the equation becomes cos phi sin square omega t plus sin omega t cos omega t sin phi. And in this first part of the equation, that is cos phi sin square omega t, the average of sin square omega t, when you see the relation sin square omega t plus cos square omega t is equal to 1. That is a usual relation, you know. Sin square theta plus cos square theta is equal to 1, and for approximately you can take it as half plus half. Half plus half will become 1. So sin square omega t is now equal to half, and when you take this expression, Here when you take the average of sin omega t and cos omega t, definitely that will become 0, because sin 0 and cos 0 will occur at products usually. So at any case this second term will become 0 and the first term will be equal to cos phi into half. So the equation is now P average is equal to Vm Im cos phi into half, and Vm can be written as that is the 2 in the denominator can be split up into root 2 into root 2. So here Vm by root 2 into Im by root 2 into cos phi. So this is nothing but Vrms Irms. So P average is equal to Vrms Irms into cos phi. RMS means root mean square velocity and root mean square current. So here what is average power? Average power is apparent power into power factor. So this is the main thing, and here the average power is also known as true power of the circuit. So from this relation you can say that average power is equal to apparent power into power factor. This cos phi is called as power factor. So now we are going to see about the special cases. There are 4 cases in this, that is resistive circuit and purely inductive or capacitive circuit, then series RLC circuit, then RLC circuit at resonance condition. These are the 4 cases we are going to see. And P average, you take this equation, P average is equal to Vrms Irms cos phi. You take that equation, and when you see this, the cos phi is equal to 1 for purely resistive circuit because angle is 0. For pure resistive circuit, the phase angle between the voltage and current is 0, and so here P average is equal to Vrms Irms. When you take purely inductive or capacitive, the phase angle is plus or minus pi by 2. You know cos plus or minus pi by 2 is equal to 0, and the P average becomes 0 in such a case. And for series RLC circuit, you know for formula, we have derived this formula, phi is equal to tan inverse XL minus XC by R. So P average is equal to Vrms Irms cos phi. When you take the particular condition as resonance, at resonance XL is equal to XC, and also the phase angle become cos 0. Cos 0 is equal to 1. So P average is equal to Vrms Irms, since the angle becomes 0 at resonance condition. The phase angle is 0. And next we are going to see about wattless current. So wattless current means the unit for power is watt. Suppose if the power consumed by a circuit is 0, then it is called as wattless current. And when you see this diagram here, Irms and Vrms, they are making an angle phi. Here the voltage is leading. So the voltage is leading means this is an inductive circuit. So this Irms is split up into 2 components, perpendicular components. And when you see this diagram, this Irms is split up into Irms cos phi and Irms sin phi. Here Irms cos phi is along the voltage and Irms sin phi is perpendicular to that Vrms, and this component cos phi component is called as active component, whereas the sin phi component is called as reactive component. And you see the 2 cases now. The component of the current Irms cos phi is in phase with the voltage and is called active component. The power in such a case is wattful current because we are having Vrms Irms cos phi. So here this is wattful current. Whereas when you take the other component Irms sin phi, that has phase angle of pi by 2 with the voltage. Here when you see here, Irms sin phi is making an angle 90 degree with Vrms. So the angle phi becomes now pi by 2, and you know cos pi by 2 is equal to 0, and so here this is called as wattless current. So the current in the circuit is said to be wattless current if the power consumed by it is 0. This is the main thing. So the current is said to be wattless if the power consumed by it is 0. So when you see this diagram, you are having 2 components, active component and reactive component. For active component it is wattful current, for reactive component it is wattless current. Watless current means the angle becomes 90 degree. So here the angle between the voltage and IRMS sin phi becomes 90 degree, and so the power factor will become 0, and so the power will become 0. So watless current means the power consumed by the circuit is 0. So when you see power factor, there are three formula for current factor. The first one is power factor is equal to cos phi, that is cosine of angle of lead or lag, and power factor is also given by R by Z, that is resistance by impedance, and power factor has another formula P average by VRMS IRMS. P average means average power. Average power is also called as true power. So true power divided by apparent power. So these three formulae represented for power factor, and the power factor is very important for a particular circuit. So power factor has some examples. When you take resistive circuit, purely inductive or capacitive circuit, and for other circuits, we are going to see that resistive circuit, for resistive circuit the phase angle is 0, and so the current is also 0. And when you see the power factor for capacitive or inductive circuit, cos is plus or minus pi by 2, that will become 0. And for other factors, power factor lies between 0 and 1 for a circuit having R, L and C in varying proportions. So three types of circuits are possible: resistive circuit, purely inductive or capacitive circuit, and RLC circuit. And for these three circuits, the power factor may differ depending upon the angle. And here advantages of AC over DC. Here first we shall see the advantage. AC is cheaper than that of DC. That is, the generation is very easy. You can easily generate AC, and transmission losses also less when compared AC with the DC, because AC can be supplied at higher voltages so that the losses can be largely prevented, and AC can be easily converted into DC with the help of rectifiers. That is the other advantage. When you say disadvantage, it cannot be used in certain applications such as charging of batteries, electroplating and electric traction, etc. In such a case you need only DC, and also at high voltages it is very dangerous to work with AC than DC, because when you see AC and DC, AC shock is attractive, so it will attract and so it will cause fatal damage. So at high voltages it is more dangerous to work with AC than DC. So these are the advantages and disadvantages of AC over DC.